we need to talk about the star that's watching us, not the sun, not our star. Another one. 640 light-years away, in the constellation Orion, visible to the naked eye every winter night as a reddish point of light marking the hunter's shoulder, Betelgeuse, a red supergiant, one of the largest stars known. If you placed it where our Sun is, its surface would extend past the orbit of Mars. It's massive, roughly 20 times the mass of the Sun. It's old for a massive star, only 10 million years, but massive stars live fast and die young. And it's dying, right now. Not in some distant future, not in billions of years like our Sun, but now. In stellar terms, Betelgeuse is on its deathbed, and when it finally exhausts its nuclear fuel and collapses, it will explode in a supernova that will be visible from Earth in broad daylight. We don't know when. Could be tomorrow. Could be 100,000 years from now. Stellar evolution models aren't precise enough to predict the timing within less than thousands of years. But it's coming. Betelgeuse will go supernova in the cosmically near future, and when it does, depending on exactly how the explosion unfolds, it could be more than just a spectacular light show. It could be a threat. Not an immediate civilization-ending threat like a gamma-ray burst or asteroid impact, but a slow, insidious threat. Radiation arriving over months and years, stripping away Earth's ozone layer, exposing the surface to deadly ultraviolet light, triggering a cascade of ecosystem collapse that we can see coming but might not be able to stop. Let's understand what we're facing. Let's map the physics of stellar death and what it means when that death occurs close enough to affect us. A supernova is the explosive death of a massive star. When a star like Betelgeuse exhausts its nuclear fuel, when it can no longer generate the heat and pressure needed to resist gravity's inward pull, the core collapses. In less than a second, it goes from the size of Earth to the size of a city, and the rebound, the shockwave from that collapse, tears through the star's outer layers at 30,000 kilometers per second. The star explodes, its outer layers containing everything the star created through fusion: carbon, oxygen, silicon, iron, and heavier elements, are blasted into space. The explosion releases more energy in seconds than the star produced in its entire lifetime. For a brief time, a single supernova can outshine an entire galaxy. From Earth, when Betelgeuse goes supernova, we'll see something unprecedented in recorded human history. The star will brighten dramatically. Over the course of days or weeks, Betelgeuse will go from being a moderately bright star to the brightest object in the night sky except for the Moon. It might reach magnitude 12 or brighter, bright enough to cast shadows at night, bright enough to be clearly visible in daylight. Imagine that. Looking up during the day and seeing two bright objects, the Sun, and a new star that wasn't there before. A star so bright it's unmistakable, so bright it dominates the sky, so bright that everyone on Earth will see it and know something extraordinary has happened. The first response will be wonder, or this is one of the most spectacular astronomical events possible, and it's happening close enough for us to see in incredible detail. Telescopes will observe the expanding shockwave, the brightening and fading of different spectral lines, the formation of the remnant neutron star or black hole. Scientists will gather data that will transform our understanding of stellar evolution. But underneath the wonder, there will be fear, because we'll know what's coming. Not immediately. Light travels faster than the dangerous radiation, but eventually. The supernova will produce X-rays, gamma rays, and cosmic rays. And while 640 light-years is far enough that we won't be in the lethal zone, it's close enough that we'll receive significant radiation, doses over the months and years following the explosion. Let's walk through what happens week by week, month by month, as Betelgeuse dies and Earth experiences the consequences. Week 0, Day 1. Astronomers notice something unusual. Betelgeuse's brightness is increasing, not by a little, by a lot, orders of magnitude. Within 24 hours, it's gone from magnitude 0.5, moderately bright, to magnitude 5, brighter than Venus at its brightest. The announcement spreads rapidly. Betelgeuse is going supernova. Social media explodes. News channels interrupt regular programming. People go outside to look at the sky, to see this star that's suddenly bright enough to be obvious, even to those who never pay attention to astronomy. And it keeps brightening. Day 2. Betelgeuse is now magnitude 8. Brighter than anything in the night sky except the moon. Bright enough to cast faint shadows. Bright enough that you can see it during the day if you know where to look. Scientists are scrambling to observe. Every telescope on Earth and in space is pointed at Betelgeuse, or will be as soon as it rises above their horizon. The data is extraordinary. Spectral lines showing the star's outer layers being blown away at thousands of kilometers per second, temperature spikes as shock waves heat the ejected material, the first hints of the intense radiation being produced at the explosion's core. And they're calculating, modelling, trying to predict what comes next. How bright will it get? How long will it last? And most importantly, what are the radiation levels going to be when the high-energy photons arrive? Day 3. Betelgeuse peaks at magnitude 12. It's now the brightest object in the night sky, outshining the moon. During the day, it's clearly visible, a brilliant point of light that you can see without any optical aid, without looking in any particular direction, because it's bright enough to catch your eye wherever you look. The world is watching. Betelgeuse has become the most observed astronomical event in human history. Billions of people are looking at the sky, seeing this impossibly bright star, understanding at some level that they're witnessing the death of an object so large it could swallow Mars, happening in real time, or rather happening 640 years ago but reaching us now. And the scientists have their preliminary models. The news is concerning. The supernova is producing enormous amounts of high-energy radiation. X-rays, gamma rays, cosmic rays. At 640 light-years distance, most of this will be absorbed or deflected by space, by Earth's magnetosphere, by the atmosphere, but not all of it. Some will get through, and the cumulative dose over months and years could be significant. Significant enough to damage the ozone layer. Significant enough to affect life on Earth's surface. Not immediately lethal. This isn't a gamma-ray burst, but dangerous. Potentially catastrophic if the exposure is prolonged. Week 1, Betelgeuse is still bright, but it's beginning to fade. This is normal for supernovae. There's an initial peak as the shock wave heats the outer layers, then a decline as the material expands and cools. Over the coming months, it will fade from naked eye visibility, though it will remain an impressive object in telescopes for years. But the radiation is arriving. The first X-rays and gamma rays from the explosion are hitting Earth's upper atmosphere. They're being absorbed by air molecules, creating cascades of secondary particles, ionizing the upper atmosphere in ways that affect radio communications. The immediate effects are minor, some satellite disruptions, some radio interference, nothing civilization threatening. But the scientists are watching their models, running simulations, and the long-term projections are worrying. The supernova is going to keep producing high-energy radiation for months. Not at the same intensity as the initial explosion. That brief, brilliant peak is over. But a sustained emission of X-rays and cosmic rays from the hot, expanding debris and the neutron star that's probably forming at the core. And that sustained emission is going to slowly, gradually, inexorably destroy Earth's ozone layer. Month 1. Betelgeuse has faded to magnitude 2, still brighter than any star normally visible but no longer dominating the sky. The wonder has faded too, replaced by concern as the radiation models are refined and the picture becomes clearer. Earth's ozone layer is being bombarded by high-energy photons. When X-rays hit ozone molecules, they break them apart, creating oxygen atoms and nitrogen oxides. the same chemistry that happens during gamma-ray bursts, but slower, more sustained, accumulating over time. The ozone depletion is measurable. Not catastrophic yet. We're talking about a few % reduction globally, more at higher latitudes where the radiation impacts are strongest. But it's growing. The bombardment continues, the chemistry continues, and the ozone layer doesn't recover as fast as it's being destroyed. Scientists project that if the radiation continues at current levels for another 6 months, ozone depletion could reach 20–30% globally. If it continues for a year, 40–50%. And at those levels, the consequences for surface life become severe. Without ozone, ultraviolet radiation from the sun reaches the surface unfiltered. UVB and UVC, the highest energy UV that's normally completely blocked, would penetrate to ground level. This radiation is sterilizing. It damages DNA, kills bacteria and algae, causes sunburn and skin cancer in humans, inhibits photosynthesis in plants. The models predict that at 40% ozone depletion, UV levels at the surface would be high enough to significantly impact ecosystems. Coral reefs would bleach, phytoplankton populations would crash, crop yields would decline, humans would need to avoid sun exposure or risk serious radiation burns, and at 50% depletion or more, the effects would be catastrophic. Ecosystem collapse, agricultural failure, mass extinction of species that depend on surface exposure or shallow water habitats. The question is, how long will the radiation continue? How long will Betelgeuse's remnant keep bombarding us with X-rays and cosmic rays? The answer depends on what's left behind. If the core collapse produced a neutron star, a stellar remnant so dense that a teaspoon of its matter would weigh 1 billion tons, that neutron star will be hot, will be rotating rapidly, will be generating powerful magnetic fields, and those magnetic fields will accelerate particles to near light speed, creating beams of radiation that sweep across space as the neutron star rotates. If one of those beams happens to point toward Earth, we'll experience pulses of radiation every time the neutron star rotates, potentially many times per second. And this will continue for years, decades, possibly centuries as the neutron star gradually cools and its rotation slows. If the core collapse produced a black hole instead, if Betelgeuse's core was massive enough that not even neutron degeneracy pressure could resist gravity, the radiation might be less sustained. Black holes don't produce the same kind of long-term emission as neutron stars. We might get a brief intense period during the collapse, then a decline as the surrounding material falls in and the system quiets. We don't know which it is. We won't know until we've observed the remnant for months or years, until we've mapped its emissions and behaviour. And by then, the damage to the ozone layer might already be severe. Month 3. The ozone depletion has reached 15% globally, 25% at high latitudes. UV levels at the surface are measurably elevated. Governments are issuing warnings: minimise sun exposure, use high SPF sunscreen, wear protective clothing. But these warnings are for humans. We can adapt, can change our behaviour, can protect ourselves. Plants can't. Animals can't. The ecosystems are beginning to show stress. Phytoplankton populations in the upper ocean are declining. These microscopic organisms form the base of marine food webs and produce a significant fraction of Earth's oxygen. They need sunlight for photosynthesis, but they are evolved for normal UV levels. The increased radiation is damaging their cells faster than they can repair. As phytoplankton decline, the species that feed on them, small fish, krill, other zooplankton, begin to decline too. The cascade is starting. The marine food web is destabilizing from the bottom up. On land, forests at high latitudes and high altitudes, where UV exposure is already higher, are showing signs of stress. Needle browning in conifers, leaf damage in deciduous trees, reduced photosynthesis leading to slower growth, and humans are beginning to experience direct effects. Skin cancer rates are rising. Eye damage, cataracts, photokeratitis is becoming more common. People who work outdoors are at highest risk, but even those who limit sun exposure are experiencing more UV damage than normal. The economic impacts are mounting. Agriculture is struggling. Crops are receiving radiation damage. Yields are declining. The fishing industry is facing collapse as marine ecosystems unravel. Tourism has crashed. Nobody wants to vacation under a sun that causes radiation burns. And it's all happening slowly enough that people can see it coming, can watch it develop, but fast enough that adaptation is difficult. We're trying to respond, developing UV-resistant crop varieties, building covered agriculture, fishing deeper waters where phytoplankton are less affected. But these adaptations take time, take resources, and they're happening while the radiation continues, while the ozone layer continues to decline. Month 6. Ozone depletion has reached 30% globally, 45% at high latitudes. The situation has gone from concerning to critical. UVC radiation is now reaching the surface, in measurable quantities. This is the highest energy UV, normally completely blocked by ozone, so deadly to biological tissue that it's used for sterilization. Even brief exposure causes severe burns, DNA damage, rapid cell death. Going outside during peak sun hours is dangerous. Not you should wear sunscreen dangerous. You will receive radiation burns within minutes dangerous. Exposed skin reddens, blisters, peels. Eyes can be damaged permanently. The only safe option is to cover all exposed skin or stay indoors. Ecosystems are collapsing. Coral reefs are experiencing mass bleaching events. Phytoplankton populations have crashed by 60% or more in the most affected regions. Fish populations are plummeting. Marine mammals are starving. Seabirds are dying by the millions. On land, forests are dying back. Grasslands are turning brown. Agricultural production has dropped by 40% globally as crops fail from UV damage and lack of pollinators. Insects are particularly vulnerable to UV, and pollinator populations have crashed. Famine is beginning. Not everywhere, not all at once, but spreading. Regions that depend on local agriculture, that can't import food from less affected areas, are experiencing food shortages. Prices are spiking, supply chains are straining, and the radiation continues. Year 1. It's been 12 months since Betelgeuse exploded. The star itself has faded to magnitude 5 or 6. Still visible to the naked eye under dark skies, but no longer the spectacle it was. What remains is a brilliant nebula, expanding at thousands of kilometers per second, glowing from the energy of the explosion and the radiation from whatever remnant formed at the core. And that remnant, we know now what it is: a neutron star. Rotating 30 times per second, generating magnetic fields trillions of times stronger than Earth's, accelerating particles to 99.9% of light speed, and beaming them out in narrow cones that sweep across space as the star spins. We're not in the direct path of those beams. If we were, we'd be experiencing gamma-ray burst levels of radiation. But we're close enough that we're catching the scattered radiation, the particles that leak out beyond the main beams, and it's enough. More than enough. The ozone layer is down to 40% of its pre-supernova level. UV radiation at the surface is 4 to 5 times higher than normal. Life has adapted to normal UV levels over billions of years. It can't adapt to this increase in 12 months. The biosphere is in full collapse. Ocean dead zones are expanding. Regions where phytoplankton die-off has created oxygen-depleted water that can't support fish or other marine life. These zones now cover 30% of the ocean surface and are growing. Terrestrial ecosystems are transitioning to new impoverished states. Forests have become scrublands. Grasslands have become deserts. The species that remain are those that can tolerate high UV. Some fungi, some bacteria, some deep burrowing animals, some nocturnal species that avoid daylight entirely. But the complex ecosystems, the food webs that support large animals and human agriculture, are gone. destroyed not by fire or flood, but by radiation from a star that died 640 years before humans invented the telescope. The human population is experiencing its own collapse, not from direct radiation deaths. We're smart enough to stay out of the sun, to build UV-shielded habitats, to adapt our behaviour. But from starvation, as agriculture fails, from disease as malnutrition weakens immune systems, from violence as desperate populations compete for declining resources. The global population, which was 8 billion before the supernova, has dropped to perhaps 5 billion, maybe less. Exact numbers are impossible. Communication networks are strained, many regions have stopped reporting, and chaos makes census taking irrelevant. Those who survive are clustered in areas with some protection, underground facilities, heavily shielded buildings, regions where the ozone depletion is slightly less severe. They're living on stored food, on hydroponics and indoor agriculture, on fishing in the deep ocean where some life persists. But these are temporary solutions. The stored food will run out. The hydroponics require energy and maintenance. The deep ocean ecosystems are stressed too, declining as their food sources from the surface disappear. And the neutron star continues to radiate. The models suggest it will remain active for decades, perhaps centuries, before it cools enough that its emissions drop to levels that allow ozone recovery. Decades or centuries. Far longer than our food stores will last. Far longer than our technological civilization can maintain itself in underground bunkers and shielded habitats. We're watching our world die in slow motion, killed by light from a star that lived and died before we existed, and there's nothing we can do to stop it. Year 2, the ozone layer has stabilized. At about 35% of pre-supernova levels, it's not declining as fast anymore. There's less ozone left to destroy, and what remains is in layers of the atmosphere where the radiation has less effect. But it's also not recovering. The neutron star continues its emissions, continues to pump radiation into Earth's atmosphere, preventing any significant ozone regeneration. UV levels at the surface have plateaued at about 5 times pre-supernova levels. This is the new normal. This is what Earth is now. A planet with a compromised atmosphere, with surface conditions hostile to most complex life, with ecosystems that have collapsed and won't recover until the radiation stops. The human population has dropped below 3 billion. Starvation is the primary killer. Agriculture is limited to heavily shielded greenhouses and underground facilities, and production is a fraction of what's needed to feed billions. Rationing is universal where governments still function. In areas where governance has collapsed, it's subsistence living or death. There are no easy solutions. We can't deflect the radiation. It's coming from all directions as the neutron star spins and it's travelling at light speed. We can't wait it out. The neutron star will remain active far longer than our civilization can survive underground. We can't leave Earth. Not at scale. We have spacecraft, space stations, a few thousand people living off-world. But evacuating billions is impossible with current technology. We're trapped on a planet that's being slowly sterilized by radiation from a dead star. Some scientists propose desperate measures. Could we artificially regenerate the ozone layer? Pump ozone-producing chemicals into the stratosphere? Create artificial atmospheric layers to block UV? The calculations are daunting. We'd need to produce ozone at rates comparable to what the entire atmosphere naturally produces, and we'd need to do it continuously because the neutron star radiation is destroying it as fast as we could create it. The energy requirements are enormous. The resources needed are beyond what our diminished civilization can muster. Others propose adaptation, engineer UV-resistant crops, develop protective technologies for humans, build covered cities, artificial ecosystems that can function without exposure to direct sunlight. These are more feasible but still difficult. Genetic engineering takes time we don't have. Building infrastructure requires resources and coordination that are scarce. And even if we succeed, we'd be consigning humanity to a future of living in artificial environments cut off from the natural world, permanently changed by a cosmic event we couldn't prevent. Year 5. The global human population is below 1 billion. The die-off has slowed. Most of those who are going to die from starvation and disease have died. Those who remain are in stable situations, sustainable at least in the short term. Underground cities have formed, networks of tunnels and chambers shielded from UV, powered by geothermal or nuclear energy, growing food in artificial light. These are humanity's ark, the preserves where civilization might survive long enough for conditions on the surface to improve, if they ever do improve. The neutron star shows no signs of slowing. It's still rotating 30 times per second, still generating powerful magnetic fields, still accelerating particles to relativistic speeds. The models now suggest it could remain active for 1,000 years or more. 1,000 years of depleted ozone, 1,000 years of high UV at the surface, 1,000 years for humanity to survive underground, maintaining technology and knowledge, waiting for the day when the surface might be habitable again. Can we do it? Can a civilization persist for 1,000 years in artificial environments, cut off from the biosphere, dependent entirely on technology for survival? History suggests it's difficult. Civilizations rise and fall on timescales of centuries. Technologies are forgotten when the people who understand them die. Knowledge is lost when libraries burn or databases fail. But we don't have a choice. The alternative is extinction. So we try. We maintain the underground cities. We teach the next generation how to grow food in hydroponic systems, how to recycle air and water, how to maintain the machines that keep us alive. We preserve what we can of human knowledge and culture, hoping that when the radiation finally stops, when the surface becomes habitable again, there will be someone left who remembers how to rebuild. Let's talk about what we could have done differently, because Betelgeuse going supernova wasn't a complete surprise. We knew it was a dying star. We knew it could explode at any time. We had warnings, had models, had predictions, but we didn't know when. And we didn't know exactly how dangerous it would be until it happened. Could we have prepared better? Built underground shelters in advance, stockpiled food, developed UV-resistant agriculture before we needed it? Maybe. But preparation requires resources and political will. It requires convincing governments and populations to invest in protections against an event that might not happen for thousands of years, or might happen tomorrow, and we can't predict which. This is the challenge of low probability, high consequence risks. They're real, but they're not immediate. The urgency isn't there. Other problems demand attention. And so we postpone, we defer, we hope we get lucky and the catastrophe doesn't occur during our lifetimes. Betelgeuse was a known risk. We watched it dim in 2019 to 2020 and wondered if it was about to explode. It didn't. It was just dust obscuring the star. But it reminded us that the threat was real, that Betelgeuse could go supernova at any time, and still we didn't prepare adequately. We continued our research, improved our models, tracked the star's behaviour, but we didn't build the shelters, didn't develop the resistant crops, didn't create the infrastructure that might have allowed us to survive the aftermath. Why not? Because it was expensive, because it was uncertain, because there were always more pressing concerns, because humans are optimists, and we assumed we'd have warning, would have time to respond, would figure something out when the moment came. We were wrong. The warning was minimal, days between when the explosion became obvious and when the dangerous radiation began affecting Earth's atmosphere. And our responses were improvised, reactive, inadequate to the scale of the crisis. We could have done better, should have done better, but we didn't, and now we're living with the consequences, or rather dying with them, slowly over years and decades, as our world becomes uninhabitable and our population dwindles to whatever can survive in artificial environments. Let's talk about the psychological impact of watching your world die over years, because this is different from sudden catastrophes like asteroid impacts or nuclear war. With sudden catastrophes, there's shock, trauma, grief, but also a kind of clarity. The event happens, you survive or you don't, and then you adapt to the new reality. But with Betelgeuse, the catastrophe is slow. You watch it unfold over months and years. You see the ozone measurements decline. You see the UV levels rise. You see ecosystems collapse piece by piece, species by species. You watch the ocean dead zones expand, the forests die back, the agricultural yields drop. And you know what's coming. You can predict, with reasonable accuracy, where this is going. You know that in 6 months the UV will be higher. In a year, higher still. In 5 years, most surface life will be gone. In 10 years, only extremophiles and humans in shelters will remain. This creates a unique form of grief, anticipatory grief for a world that's dying in front of you that you can see and touch and remember, but that you know won't exist in recognizable form much longer. Some people can't handle it. Depression and suicide rates spike. Why continue when the future is so bleak, when everything you've known is disappearing, when your children will grow up in underground bunkers, never seeing the sun or the sky or the natural world? Others find purpose in the struggle. They work to build the underground cities, to preserve knowledge, to create systems that might allow humanity to survive. They find meaning in the effort, even if the outcome is uncertain. And some become numb. They go through the motions, survive day to day, not thinking too much about the future, because thinking about it is too painful. They exist, but they're not fully alive, not fully present. They're waiting, though for what they couldn't say. The psychological toll is enormous. Humanity is experiencing collective trauma, collective grief, collective fear about a future that's fundamentally different from anything in our evolutionary history. We're not adapted for this. We're not built to watch our biosphere die while remaining cognitively aware of what's happening and why. And we're dealing with it as best we can, which is to say, poorly. Mental health systems are overwhelmed. Communities are fractured. Trust is low. When resources are scarce and the future is uncertain, cooperation breaks down and people look after their own first. This is what it means to live through a slow apocalypse. Not the dramatic end of the world in fire and fury, but the gradual unwinding of everything that makes Earth habitable, while you're fully conscious and aware and helpless to stop it. Let's think about what survives, because even in this scenario, some life persists, some ecosystems adapt, some species find ways to continue. Deep ocean life is less affected. The UV doesn't penetrate deep water. Ecosystems around hydrothermal vents, in the abyssal plains, in the deep trenches, these continue largely as before. They depend on chemosynthesis rather than photosynthesis, on energy from Earth's internal heat rather than from the sun. The supernova radiation doesn't significantly affect them. Cave ecosystems survive. Underground rivers, subterranean lakes, the darkness where UV can't reach, these remain habitable. The species that live there, adapted to eternal darkness, continue their existence unaware that the surface world has changed. Some microorganisms survive on the surface, extremophiles, bacteria and archaea that can tolerate high radiation, that have protective mechanisms against UV damage, that can repair DNA faster than it's being damaged. These hardy species inherit the Earth's surface, at least temporarily, and humans survive in our artificial environments in our underground cities. We're no longer the dominant surface species. That role has been vacated, at least until the radiation subsides. But we persist, maintaining our technologies, our knowledge, our cultures in the sheltered spaces we've created. This is Earth after Betelgeuse, a planet with a compromised atmosphere, with surface ecosystems reduced to extremophiles and deep ocean life, with humanity driven underground, waiting for conditions to improve. It's not total extinction. It's not the end of all life, but it's a profound transformation, a fundamental change in what Earth is and what can survive here. And it's all because a star 640 light-years away ran out of fuel and collapsed. Not aiming at us, not even where we exist, just following the laws of physics, dying as all stars eventually die, and happening to be close enough that its death affects us. Let's talk about the neutron star itself, because it's now a permanent feature of our sky, a reminder of what happened and what continues to happen. You can see it if you have a telescope and know where to look. It's in Orion, where Betelgeuse used to be. It's not visible to the naked eye, neutron stars are too small, too dim, but in X-ray wavelengths, it's brilliant. A pinpoint of intense radiation, pulsing 30 times per second as it rotates. Astronomers watch it obsessively, measuring its pulse period, tracking its gradual slowdown as it loses rotational energy, monitoring its emissions for any change that might indicate the radiation is weakening. Because that's what we're hoping for. Eventually, decades, centuries, millennia from now, the neutron star will cool, its rotation will slow, its magnetic field will weaken, and its radiation emissions will drop to levels that allow Earth's ozone layer to recover. When that happens, when UV levels at the surface drop back toward normal, life can begin to reclaim the surface. Plants can grow again, ecosystems can rebuild, and humans can emerge from underground, can return to the surface, can try to restore what was lost. But that day is far in the future. The neutron star shows no signs of slowing significantly. Our models suggest thousands of years before its emissions drop enough to matter. Thousands of years of underground living. Thousands of years of maintaining technological civilization in artificial environments. Thousands of years of waiting for a star to cool enough that our world can live again. Can we do it? Can humanity survive that long under those conditions? Can we maintain the knowledge, the technology, the social cohesion required to keep the underground cities functioning for dozens of generations? We don't know. We're trying. We're teaching our children, preserving our knowledge, maintaining our systems. We're hoping that we're resilient enough, adaptive enough, determined enough to survive until the surface becomes habitable again. But hope isn't certainty. And the history of civilization suggests that maintaining complex societies across many generations is difficult under the best circumstances. Under these circumstances, with resources scarce, with the surface world dead, with the psychological burden of knowing we're trapped underground for thousands of years, it might be impossible. We'll find out. We don't have a choice. We survive underground for millennia, or we go extinct. Those are the options Betelgeuse has left us. Let's shift perspective now. Let's move from the immediate catastrophe to the deeper questions about what it means to exist in a galaxy where stars die, where those deaths can affect worlds light years away, where cosmic processes we can't control determine whether civilizations survive or collapse. Supernovae are not rare in the galaxy. They occur roughly once every 50 years somewhere in the Milky Way. Most are too distant to affect us, thousands or tens of thousands of light years away, far enough that the radiation dissipates to harmless levels before reaching Earth. But occasionally, rarely, a supernova occurs close, within a few hundred light years, close enough that the radiation, while not immediately lethal, is enough to affect planetary atmospheres, to damage ozone layers, to change the conditions for surface life. Earth has been affected before. The geological record shows evidence of possible supernova impacts, layers of iron-60 isotope in ancient sediments, suggesting that radioactive debris from nearby supernovae reached Earth and settled into the ocean floor. These events occurred millions of years ago, at times when mass extinctions or significant ecosystem changes were happening. We can't prove causation. The evidence is suggestive but not conclusive. But it's consistent with the idea that nearby supernovae have affected Earth's biosphere multiple times over geological history, that what's happening now with Betelgeuse has happened before and will happen again. This places our current crisis in context. We're not being singled out, not being punished, not experiencing something unique. We're just in the wrong place at the wrong time, living in an era when a nearby star happens to die, when its death happens to produce conditions that threaten complex surface life. It's natural, it's expected, it's part of living in a galaxy where stars are born, live, and die on timescales that overlap with the evolution of life and civilizations. But natural doesn't mean acceptable. Expected doesn't mean tolerable. We can understand why Betelgeuse exploded, can place it in the context of stellar evolution and galactic ecology, while still grieving for what we're losing, still fighting to survive, still hoping we can endure until conditions improve. Let's talk about what makes Betelgeuse's supernova different from a gamma-ray burst or other cosmic threats we've discussed. Gamma-ray bursts are instant. You have no warning, and the lethal radiation arrives at the same time as the light that tells you it's happening. It's over in seconds or minutes, and either you survive the immediate effects or you don't. Betelgeuse is slow. We had warning, admittedly only days, but warning nonetheless. The dangerous radiation builds up over weeks and months. The ozone depletion happens gradually. The ecosystem collapse is progressive, allowing time to observe, to measure, to understand what's happening even if we can't stop it. This slowness is both mercy and curse. Mercy because we have time to adapt, to build shelters, to preserve what we can. Curse because we have to watch, have to experience months and years of watching our world die, knowing what's coming, unable to prevent it. It's like being diagnosed with a terminal illness versus dying in an accident. The accident is sudden, shocking, but at least it's quick. The illness gives you time to prepare, to say goodbye, to come to terms with death. But it also gives you time to suffer, to experience anticipatory grief, to watch yourself decline. Betelgeuse's supernova is Earth's terminal illness. We're dying, but slowly, with full awareness of what's happening and why, and that awareness is its own form of suffering. Another difference, gamma ray. Bursts and most cosmic threats are one-time events. They happen, they're over, and then conditions either recover or they don't. But Betelgeuse has left behind a neutron star that will continue affecting us for thousands of years. It's not a brief catastrophe, it's a permanent change in our cosmic environment. The neutron star is now a neighbour, a source of ongoing radiation, a persistent threat that won't go away until it cools, and that cooling will take longer than human civilizations typically last. We're not just dealing with a disaster, we're dealing with a new reality, a transformed cosmic neighbourhood where one of our nearby stars has become a source of deadly radiation. And we have to adapt to that reality, have to find ways to survive in it for far longer than we initially anticipated. Let's think about other stars, other potential supernovae, because Betelgeuse is not the only candidate. Eta Carinae, 7,500 light-years away, is even more massive than Betelgeuse. It's already experienced massive eruptions. In the 1840s, it briefly became the second brightest star in the sky, after an outburst that expelled more than 10 solar masses of material. It's unstable, dying, and when it goes supernova it will be spectacular. But it's far enough that the radiation shouldn't be dangerous. 7,500 light-years is more than 10 times farther than Betelgeuse. The inverse square law means radiation intensity drops off rapidly with distance. What's lethal at 6 to 40 light-years is merely interesting at 7,500. Spica, in Virgo, is 250 light-years away. It's actually a binary system, two massive stars orbiting each other. Both will eventually go supernova, though not necessarily at the same time. When they do, at 250 light-years, the radiation could be concerning. Not Betelgeuse level, but enough to cause some ozone depletion, some ecosystem stress. And there are others, Antares in Scorpius, Rigel in Orion, various massive stars within a few hundred light-years, any of which could explode and affect Earth to some degree. We're living in a galaxy with thousands of potential supernovae. Most are harmless because of distance, some are close enough to be dangerous, and we have no way to predict when any particular star will die. Stellar evolution models can narrow it down to within the next 100,000 years, but not much more precisely than that. So we're vulnerable. not just to Betelgeuse, but to any of dozens of nearby massive stars, and all we can do is watch them, measure their properties, try to predict which ones are closest to death, and hope none of them explode in the near future. Hope is not a strategy, but when you're facing threats you can't prevent or control, hope is sometimes all you have. Let's talk about consciousness again, about what it means to be aware in a universe where your biosphere can be damaged by events light years away. You exist because of stars. The atoms in your body were forged in stellar furnaces. Carbon, nitrogen, oxygen, iron, all created through fusion in the stars that lived and died before the solar system formed. You're made of stardust, literally, assembled from the debris of ancient supernovae. But stars also threaten you. The same processes that created your atoms can destroy the conditions that allow those atoms to organize into living systems. Supernovae giveth, and supernovae taketh away. There's a bitter irony in that. You owe your existence to stellar death, but stellar death can also end your existence. The universe creates you through violent processes and can destroy you through the same processes, and there's no malice in either, just physics, following its laws, indifferent to consequences. This is humbling. You're not separate from the cosmic processes that threaten you. You're part of them. A temporary configuration of matter created by stars and vulnerable to stars, existing in the brief moment between stellar creations and stellar destructions, and yet you're aware. You can understand this. You can know that you're made of stardust, can appreciate the irony that your creator is also your potential destroyer, can contemplate your place in these grand cycles. That awareness doesn't protect you. Knowing why Betelgeuse exploded doesn't stop the radiation from destroying your ozone layer. Understanding stellar evolution doesn't bring back the ecosystems collapsing under UV bombardment, but awareness is valuable anyway. It's what makes you more than just matter. It's what allows you to know, to understand, to find meaning even in catastrophe. The universe produces consciousness through stars and threatens consciousness through stars. And the conscious beings get to experience both sides of that paradox, get to be grateful for existence while grieving its fragility, get to appreciate creation while confronting destruction. That's what it means to be human in a universe of dying stars, to hold both truths simultaneously, to be made of stellar debris and threatened by stellar debris, to understand the processes that could kill you while remaining present enough to experience life despite that understanding. Let's drift toward contemplation now, toward accepting supernovae not as immediate threats, but as part of the larger cosmic context we inhabit. Stars die. This is not abnormal. This is not a breakdown of natural order. This is how stellar evolution works, how elements heavier than hydrogen and helium get created and distributed through space, how the galaxy recycles matter and energy. Every star massive enough will eventually exhaust its fuel and explode. Every star like Betelgeuse, like Rigel, like Spica, will one day become a supernova. It's written in their mass, determined when they formed from collapsing gas clouds billions of years ago. We happen to live near some of these stars, not by choice, not by design, just by the accident of where the solar system formed and where it's orbited over the past 4.6 billion years. We're neighbours to stars that will die violently, and sometimes those deaths affect us. This is the cost of living in a galaxy. You get the benefits, heavy elements, complex chemistry, the potential for life and consciousness. But you also face the risks, supernovae, cosmic rays, radiation from stellar deaths. You can't have one without the other. The same stellar processes that make life possible also create threats to life. The universe doesn't separate creation from destruction, doesn't give you the good parts without the dangerous parts. It's all connected, all part of the same system, and you're part of it too, whether you want to be or not. Understanding this doesn't make Betelgeuse's supernova less tragic. It doesn't bring back the billions who've died or restore the ecosystems that have collapsed, but it places the tragedy in context, makes it part of a larger pattern, rather than an isolated catastrophe. We're experiencing what many worlds have probably experienced, what many worlds will experience in the future. We're not special in our suffering, not unique in our vulnerability. We're just one more planet affected by stellar death, one more biosphere struggling to survive cosmic processes it can't control. And maybe there's some comfort in that universality. We're not alone in facing this. Other civilizations on other worlds, around other stars, have probably faced similar catastrophes. Some survived, some didn't. We're part of a larger story of life persisting despite cosmic violence, or failing to persist, or adapting into new forms. Our particular story isn't finished yet. We're still here, still fighting, still trying to survive underground while the surface becomes uninhabitable. The ending isn't written. We might make it through the thousands of years until the neutron star cools. We might not. But either way, we're part of the cosmic pattern, part of the story of consciousness emerging from matter, facing threats from the same processes that created it, and either persisting or ending based on circumstances often beyond control. Let's think about the future, about what Earth might look like if and when we survive this. Assume we endure. Assume humanity maintains its underground cities for the thousands of years needed for the neutron star to cool, for the radiation to drop, for the ozone layer to recover. What then? We emerge, carefully, gradually, testing the surface conditions, measuring UV levels, ensuring it's actually safe before committing populations to surface exposure. And we find a different world. The ecosystems that existed before the supernova are gone. The species that depended on those ecosystems are extinct. What remains are the extremophiles that survived the radiation, the deep ocean life that was never affected, and the hardy generalists that managed to persist in protected niches. These survivors will be the seeds of new ecosystems. Evolution will proceed from them, filling the empty niches, diversifying into new forms adapted to post-supernova conditions. But this takes time. Millions of years for complex ecosystems to fully develop. In the shorter term, thousands of years, Earth's surface will be a simplified, impoverished biosphere. Some plants, some insects, some small animals. Nothing like the complexity that existed before. Nothing that can support large animal populations or human agriculture without significant assistance. We'll have to rebuild carefully, reintroduce species from preserved genetic stocks, cultivate ecosystems, guide their development, help them stabilize. We'll be planetary gardeners, restoring a world that was damaged by events we couldn't prevent and will remember. The supernova will be part of our history, our mythology, our cultural identity. We'll be the species that survived stellar death, that endured underground for millennia, that emerged to reclaim a world transformed by cosmic violence. That experience will shape us, our values, our priorities, our relationship with the cosmos. We'll be more aware of our vulnerability, more committed to resilience, more focused on survival across deep time. We'll also be more distributed, probably. Having experienced the near extinction from a single cosmic event affecting one planet, we'll be motivated to spread to other worlds, to ensure that no single supernova or asteroid impact or other catastrophe can end humanity. We'll become an interstellar species if we can, not to escape Earth. We'll still love our home world, we'll still work to restore it, but to ensure survival, to create redundancy, to make ourselves robust against cosmic threats by distributing ourselves across multiple star systems. This is humanity's potential future after Betelgeuse, a species transformed by catastrophe, shaped by survival, committed to resilience across cosmic timescales. If we survive, if we maintain our underground cities long enough, if we don't lose our knowledge or our cohesion or our will to persist, those are big ifs. But we're trying. We're doing everything we can to make it through. And maybe that's enough. Let's talk about meaning one more time, from the perspective of living through a slow apocalypse. When your world is dying around you, when ecosystems are collapsing and populations are plummeting and the future looks bleak, where do you find meaning? Not in permanence. Nothing is permanent, and Betelgeuse has made that abundantly clear. Not in safety. You're not safe, never were safe, never will be safe from cosmic processes that dwarf you. Meaning comes from presence, from being aware in this moment, from experiencing what's happening, from connecting with others who are also experiencing it. You're alive right now. The world hasn't ended yet, even though it's ending. There's still beauty. In the stars you can see from your underground city through periscopes and cameras, in the relationships you maintain with family and community, in the knowledge you're preserving for future generations. There's still purpose in the work of maintaining the systems that keep you alive, in teaching children about the world that was and the world that might be again, in contributing to humanity's survival even if you personally won't live to see the surface again. There's still love for the people around you, for the idea of Earth's recovery, for the dream that consciousness will persist despite the catastrophe. These things matter, not because they're permanent or because they'll echo into eternity, but because they're real, because they're happening now, because meaning exists in the experiencing of them. Betelgeuse can't take that away. It can kill you, can destroy your biosphere, can force your species underground for millennia, but it can't erase the fact that you existed, that you loved, that you found meaning in the face of catastrophe. And maybe that's the ultimate response to cosmic threats. Not victory, you can't defeat a supernova, but persistence. Not safety, you'll never be truly safe, but courage. Not permanence, nothing lasts forever, but presence. Being here, now, aware and engaged. Creating meaning in the moment despite knowing the moment is temporary. That's what consciousness does. It finds meaning in temporary experiences, creates value in fragile lives, persists despite knowing it will end. Betelgeuse exploded. Earth is dying. Humanity is surviving underground. And in that survival, in that persistence, in that refusal to give up even when the odds are terrible, there's meaning. Not cosmic meaning, the universe doesn't care, but human meaning, which is the only kind we can actually experience, the only kind that matters to us. And that's enough. Has to be enough. Because it's all we have, all we've ever had, regardless of whether stars are exploding or stable, regardless of whether our world is thriving or dying. We find meaning in the present. We persist despite uncertainty. We love what's temporary. We create value in fragile systems. That's the human response to Betelgeuse, to all cosmic threats, to the fundamental uncertainty and vulnerability of existence. And it's a worthy response, not because it saves us, it might not, but because it's true to what we are, to what consciousness is, to the experience of being aware in a universe that produces both stars and their deaths, both life and its ending. Let's move into the deepest contemplation now, into the space where the horror of Betelgeuse's supernova transforms into acceptance, where the slow apocalypse becomes part of the larger understanding of what it means to exist in a galaxy of dying stars. We've spent time with this catastrophe. We've watched Betelgeuse explode, watched the radiation arrive, watched Earth's ozone layer collapse and ecosystems fail. We've experienced the slow die-off of billions, the retreat underground, the grim reality of maintaining civilization in artificial environments for thousands of years. We've felt appropriate grief, acknowledged genuine loss, understood that our world has been fundamentally changed by an event we couldn't prevent or control. Now it's time to integrate this experience, to find peace not through denial but through perspective, through placing Betelgeuse in the full context of stellar cycles, galactic ecology, and the brief precious nature of consciousness anywhere in the universe. Start with this recognition: you're temporary, not just your individual life, that was always going to end, but your species, your biosphere, your entire planetary ecosystem. all temporary, all subject to processes you don't control, all existing in the brief moment between creation and dissolution that characterizes everything in the universe. Betelgeuse's supernova doesn't create this temporariness. It just makes it obvious, makes it immediate, strips away the comfortable illusion that your world is stable and permanent. The truth is, your world was never permanent. Earth has experienced 5 major mass extinctions, countless smaller ones. The planet has been snowball Earth, has been tropical at the poles, has seen the rise and fall of countless ecosystems. The dinosaurs had 165 million years. Humanity has had perhaps 300,000. Both are brief moments in Earth's 4.5 billion year history. And that history is itself temporary. In 1 billion years, the sun's increasing luminosity will boil Earth's oceans regardless of whether any supernovae occur. In 5 billion years, the sun will expand into a red giant and consume the planet. Earth's habitability has an expiration date. Life on Earth has an expiration date. Even if Betelgeuse hadn't exploded, even if no other cosmic catastrophes occur, the ending was always coming. Betelgeuse just moved up the timeline. Instead of billions of years, we have thousands. Instead of a slow transition as the sun evolves, we have a sudden change from stellar death. But the fundamental truth is the same. Nothing lasts. Everything ends. The only questions are when and how. Let's think about stars differently now. Not as threats, though they are that, but as the source of everything, including the consciousness that can appreciate their beauty and fear their deaths. Every atom in your body was created in a star. Hydrogen fusing into helium, helium into carbon, carbon into oxygen, all the way up the periodic table to iron and beyond. This alchemy occurs in stellar cores, driven by temperatures and pressures that would vaporize anything we can build. When stars die, when they explode as supernovae, they scatter these elements into space. Gas clouds enriched with heavy elements collapse under gravity, forming new stars and planets. Some of those planets develop conditions suitable for life. Some of that life develops consciousness. You are the universe becoming aware of itself through a chain of stellar births and deaths stretching back billions of years. You exist because stars lived and died long before Earth formed, because their deaths enriched the galaxy with the elements needed for complex chemistry, for life, for brains capable of consciousness. Betelgeuse is part of this same cycle. Its death will enrich the interstellar medium with heavy elements. In millions of years, some of that material will be incorporated into new stars, new planets, potentially new life. The universe creates through destruction. It has no other method. Everything that exists came from something else that ended. You are built from stellar ash. Your world formed from the debris of previous worlds. And when Betelgeuse's radiation destroys Earth's current ecosystems, when the species that exist now go extinct, the planet will eventually recover. New life will evolve from whatever survives. New ecosystems will develop. And billions of years from now, those ecosystems might produce new consciousness, new awareness, new beings who look at the stars and wonder about their place in the cosmos. The cycle continues. Creation, destruction, creation again. And consciousness arises wherever conditions allow, experiences existence for its brief moment, and then transitions back into the matter and energy from which it came. You're part of this cycle. Not an exception, not separate, but fully integrated into the cosmic pattern of birth and death and rebirth. And there's a kind of peace in recognizing this. Not the peace of safety. You're not safe. But the peace of understanding your place, of seeing yourself as part of something larger, of accepting that your ending is not a tragedy in cosmic terms, but simply a transition in an ongoing process. Let's talk about the light from Betelgeuse one more time, about what it means that we're watching events that happened 640 years ago. When Betelgeuse exploded, it was 1384 on Earth. The Renaissance hadn't begun, the printing press hadn't been invented. Most of the world was illiterate. Astronomy was astrology, and the stars were thought to be fixed on crystalline spheres. The light from that explosion has been travelling through space for 640 years. It crossed the vast emptiness between stars, spread according to the inverse square law, finally reached Earth in our time, and we saw it. We observed it with telescopes and instruments that would seem like magic to the people alive when the explosion occurred. We measured its spectrum, calculated its energy, understood what happened in ways the original observers never could. This is time travel, in a sense. When you look at Betelgeuse, you're seeing the past. Not your past, you didn't exist 640 years ago. But the star's past, the moment of its death, arriving at your eyes as light, as information about an event that occurred before your great-great-great-grandparents were born, and the radiation that's destroying your ozone layer, that's killing your ecosystems, is also from that same moment. The explosion is still reaching you, still affecting you, 640 years after it happened. This is what it means to live in a relativistic universe. Causes and effects are separated by light travel time. Events happen now for the star, but 640 years later for you. The distinction between simultaneous events breaks down over cosmic distances. Betelgeuse died in 1384. You're experiencing the consequences in 2024. Both statements are true, both depend on your frame of reference, and both illustrate how strange and disjointed causality becomes when light speed delays are significant. From the star's perspective, if stars had perspectives, it died, and immediately its light and radiation spread outward. From your perspective, the star was alive for most of human history and only recently died. Which perspective is correct? Both. Neither. The concept of now across cosmic distances is relative, observer-dependent, not absolute. This might seem like abstract physics, but it has profound implications for how you understand causality, time, and your relationship with the cosmos. You're not living in the same now as distant stars. You're living in your local now, your light cone, the region of space-time that can causally affect you, and that you can causally affect. Betelgeuse was outside your light cone until the moment its light reached Earth. It couldn't affect you, wasn't even a contemporaneous event from your reference frame, until its death arrived here as light and radiation. And now it's in your light cone. Now it's affecting you. Now you're experiencing consequences that originated 640 years ago. Time is stranger than everyday experience suggests, and that strangeness is part of what makes cosmic threats so disorienting. You're being affected by events that happened centuries ago, by causes that originated before you existed, by processes that were set in motion when your ancestors were barely literate. The universe operates on timescales and distance scales that make intuitive causality break down, and you have to live with that. Have to accept that you can be killed by events that happened before you were born, that took centuries to reach you, that you could never have prevented or influenced. Let's think about what happens thousands of years from now, assuming humanity survives. The neutron star has finally cooled. Its emissions have dropped to levels that allow Earth's atmosphere to recover. Ozone is rebuilding. UV levels at the surface are dropping toward normal. The first surface expeditions venture out. Scientists in protective suits, measuring radiation, testing soil and water, looking for signs that life is returning. And it is returning. Some plants have survived as seeds, dormant for millennia, waiting for conditions to improve. They're sprouting now, tentatively reclaiming the surface. Some insects have survived in protected niches. Some microorganisms have adapted, evolved resistance to radiation, and are now the foundation of new ecosystems. It's not Earth as it was. The species composition is different. The ecosystems are simpler, but it's alive. The planet is healing. Humanity begins to emerge, slowly, building surface structures, testing agriculture, gradually transitioning from underground cities to surface settlements. And we carry the memory. The The supernova is our defining historical event, the catastrophe that nearly ended us, the crisis that forced us underground for 2,000 years. It shapes our culture, our values, our understanding of our place in the cosmos. We're more humble now, more aware of our vulnerability. We've experienced directly what it means to be at the mercy of cosmic processes, to have your entire civilization threatened by an event light years away that you couldn't prevent. We're also more resilient. We've proven we can survive, can endure catastrophic changes to our environment, can maintain civilization across timescales longer than most. Civilizations have existed, and we're more determined to spread, to become an interstellar species, to ensure that no single event, no single supernova or asteroid or solar flare can end humanity. We've learned that putting all our population on one planet is existential risk. We need to be distributed, redundant, present on multiple worlds in multiple star systems. This is the gift of catastrophe, clarity, understanding what truly matters, recognizing threats you were ignoring, developing capabilities you didn't think you needed. Betelgeuse nearly killed us, but surviving it might make us stronger, might drive us to become the kind of species that can persist across geological timescales, across cosmic catastrophes, across the full lifespan of stars. If we survive, if we make it through the underground years, if we emerge on the other side still capable of space travel, still possessing the knowledge and technology needed to reach other stars, those are uncertainties, but they're the uncertainties we're working with. And working is better than despairing. Trying is better than giving up. Let's drift into silence now, into the quiet acceptance that comes when understanding becomes peace. You know about Betelgeuse. You understand stellar evolution, supernova mechanics, the cascading consequences of nearby stellar death. You've contemplated the slow apocalypse, the underground survival, the thousands of years of waiting for conditions to improve, and you can let it settle now, not forget. This is too significant to forget. But let the emotional intensity fade. Let the knowledge take its proper place alongside everything else you know about living in a dangerous universe. Betelgeuse exploded. Earth is damaged. Humanity is adapting. And life, in whatever form, will continue. The star that died gave you atoms. The star that died is also taking them back, or trying to, by destroying the conditions that allow those atoms to organize into living systems. This is the cosmic cycle. You can't escape it. You can only participate in it for as long as participation is possible, and participation is still possible. Right now, in this moment, you're alive, you're conscious, you're experiencing what it's like to exist in a universe where stars die and affect worlds light years away. That experience is real, it's valuable, it doesn't require permanence to matter, it just needs to happen, which it is, which it does, right now. Be here for it. For the underground cities, if that's where you are. For the memory of the surface world, if you remember it. For the hope of eventual recovery, if you believe in it. Be present for whatever is actually occurring in your experience, rather than dwelling on hypothetical futures or unchangeable pasts. The neutron star spins overhead, invisible to the naked eye, pulsing 30 times per second. It's a reminder of what happened and what continues to happen, but it's also just an object following physics, doing what neutron stars do. It's not malicious, it's not targeting you, it's just existing, and its existence happens to create conditions that threaten your existence. That's how the universe works. Objects exist, they interact. Sometimes those interactions support life, sometimes they threaten it. Neither outcome reflects intent or judgment. Both are just physics, and you exist in the middle of all this physics, aware of it, affected by it, unable to control most of it but capable of understanding it. That understanding doesn't save you, but it does give you perspective. You know why Betelgeuse exploded, why the radiation is dangerous, why your world is changing. You're not experiencing random catastrophe. You're experiencing natural consequences of stellar evolution, understood through science, predictable in principle if not in timing. There's dignity in that understanding, in facing your circumstances with clear eyes rather than superstition or denial, in knowing what you're up against even when you can't defeat it. Sleep now, or wake, or continue your day, carrying this knowledge lightly. Betelgeuse is in the past. The explosion happened 640 years ago. The light has arrived, the radiation is here, and the consequences are unfolding. You're living through those consequences, adapting to them, surviving them as best you can. And in that survival, in that adaptation, in that persistence despite catastrophic change, you're honouring what consciousness does. It continues. It persists. It finds meaning in temporary experiences and creates value in fragile systems. The dying star and the consciousness it threatens, both temporary, both part of the cosmic pattern, both real and valuable in their brief existence, be at peace with both, the star that gives and takes, the consciousness that receives and experiences, the universe that creates and destroys without preference, without intent, without caring. You're here, now, aware of being aware, experiencing what billions of years of stellar evolution and planetary formation and biological evolution made possible. That's extraordinary, not permanent. Nothing is permanent, not safe, nowhere is safe, but extraordinary nonetheless. A brief light in the darkness, a temporary organisation of matter into consciousness, an awareness that knows it's temporary and finds meaning anyway. That's you, that's humanity. That's what we do in the face of dying stars and collapsing ecosystems and uncertain futures. We persist, we adapt, we find meaning, we create value, we love what's temporary and build despite knowing it won't last. The universe produces consciousness through stars and threatens consciousness through stars. And consciousness, wherever it arises, does what it does. Experiences, understands, creates meaning, persists for as long as conditions allow. Betelgeuse can't change that, can only end it eventually, or force it to transform, to adapt, to continue in new forms, in new environments. And until that ending or transformation comes, there's awareness, there's experience, there's the extraordinary fact of being conscious in a universe of dying stars. Rest in that fact, not in false promises of safety, but in the reality of present awareness. The star died centuries ago. You're experiencing it now. And in that experience, in that awareness, the universe knows itself, knows its own violence and beauty, knows what it's like to be affected by stellar death. You are that knowing. For now, for as long as now lasts, for as long as consciousness persists despite the radiation, despite the damage, despite the slow transformation of your world. That's enough. That's everything. The dying star and the living consciousness, connected across 640 light years by photons and radiation, by cause and effect stretched across time and space, both temporary, both part of the same cosmic story, both extraordinary in their brief existence. Be grateful for the connection, for the atoms the star provided, for the consciousness those atoms enable, for the awareness that can understand the star's death, even as that death threatens the awareness itself. This is the gift and the curse of consciousness, to know, to understand, to experience both creation and destruction, both beauty and horror, both the star that makes you possible and the star that makes you vulnerable. Hold both, accept both, be present for both. The universe is vast and strange and dangerous and beautiful. You're a small part of it, temporary and fragile, but real and aware and capable of creating meaning. Create it, experience it, be it, for as long as you can. The star has died. The consciousness persists. And in that persistence, brief as it is, the universe achieves something remarkable. awareness of itself, understanding of its own processes, meaning created from matter and energy, and the strange phenomenon of consciousness. You are that meaning, that awareness meaning, that brief, impossible, precious experience of being conscious in a universe of dying stars. Be here for it, fully, completely, for as long as here is possible, which is now, which is always enough.